All right, so the recorder is on. Everything from now on is going to be recorded. And what we'll do today is the first thing is to clarify the due date of the function calls assignment as opposed to the program submission. So the function calls assignment or lab is supposed to be due on Tuesday, but apparently when I said it, I said it in a confusing way. So I will kind of postpone it so that people can turn it in today. Um, the actual program that you have to turn in is due on December 6th, which is next Tuesday. All right. But I would not kind of sit on this one because this program looks easier than it really is. So it's actually, it's a good test of whether you understand the concepts or not. I'll put it that way. And then we are going to start to talk about structures and arrays in today's class. Um, and then we also have a lab that is kind of in the same format. This one here is due today. The lab itself is due today. But the code submission is due next Thursday. So we do have two programming projects that are overlapping between now and the last lecture of the entire semester. Because next Thursday is the last lecture of this class, and I will talk about a quick review of the exam in spring 2022. So this way you get an idea. You can get an idea of the test format from the last semester. Note that I'm very carefully avoiding to say anything about what it is going to look like this semester. I kept saying this is what it was like last semester. Alrighty. So with that all said, do we have any questions about past concepts? Like, has anyone tried to work on the swap subroutine? And are there any questions about the attempt to work on the swap subroutine or function or module? Those are all terms of the same, referring to the same thing. No questions? All right. Well, if there are no questions, we are moving forward to talk about structures. So, structures and pointers is kind of the focus of today's lecture, as well as the lab of today, and also the programming project that is due. Okay, let me see. Am I pointing at the right thing? Nope, here. So the actual program is due on December 8th, which is 1 week from today. And once again, this is not going to be a major heavy duty kind of project if you understand the concepts. On the other hand, for people who are having trouble understanding the concepts, making the connection between assembly code to what the stack looks like, how we utilize the stack to the C concept that we're translating, this one can be a little bit more of a challenge. Okay, so that's why there's a week. And so far, nobody has made use of my office hours. So if anyone has questions about the material, you're more than welcome to use the office hour, which is right before this lecture. I also have office hours tomorrow, and also on the other 2 days, Mondays and Wednesdays. So I would say use those office hours if you need any help with the material. Also in terms of how to prepare for the exam and stuff like that. All right. With all that said, I'm going to get started with structures and arrays in TTP ASM. And this is a module that I just recently wrote. Um, so in an architecture with a memory of multiple bytes, items. So what this means is memory bandwidth, I should say memory bandwidth of multiple bytes. So these are the architectures where one memory fetch would actually return multiple bytes, like 8 bytes with 64-bit architecture. So in those cases, items in an array are usually aligned to the memory width. So that's it really is just saying that there will be some wasting of space when we are allocating for arrays. It does not really concern us because the TTP or text toy processor is is a 8-bit processor. So each memory access actually only access 1 byte. So there's no actual concern about this. So you basically just have to add the index. So depending on what buffer is, um, we have this equation here. V is the ceiling of the size of a certain type divided by W times W, which means we size it up to multiples of W, and W is the word size or the width of the memory bus of a computer system. But since TTP only has W equaling to 1, so that means whatever type X is also what V is. So there's no upsizing, there's no rounding up to the next multiple of W's. So it's a non-concern for us, okay? But I'm just saying that for architectures where W is 8 or something like that, some compilers would actually compile code to make use of multiple of W's for arrays. And then for structures, it's kind of the same deal. Basically, this is just talking about how do we maintain structures. This is actually new. I think the best way for me to illustrate how structures are translated into assembly language is to use a program to illustrate it. So that's what I'm going to do, is to use a program to illustrate how structures are utilized in assembly language. Let me go to a text prompt like this one, and then we'll go ahead and take a look at a few sample programs. So we'll go ahead and take a look at, I'm thinking whether to use the same sample program as on my Mondays and Wednesday class. I suppose that one is going to be okay, especially just the C code. I will go ahead and re-implement the assembly code. Let me remove the assembly code first. So I think that one is called struct.ttpasm. All right, so we'll take a look at the C code, and then we'll go ahead and construct the TTPASM or the assembly code, kind of gradually. All right, so on the left-hand side, we see the C code, and on the right-hand side, it's empty because I'm going to give you the assembly code corresponding to that C code. So we'll work on the C code first, line by line, until we get to the point of, we kind of know what the C code is supposed to do. And then at that point, we'll go ahead and get started with the assembly code. Line 3 to line 7 in the C code is the definition of a structure. If you do not know what a structure is, but you know what a class is, a structure is basically a primitive class. With a class, you can have methods, which are basically functions defined as a part of a class. You cannot do that with a structure, not in C, because C does not have true object-oriented programming concepts. With a class, you can declare members to be public, which means everybody can get to see those members. You can declare members to be protected, which means only the class, only the class itself and all the derived classes can see it, but not from outside of the inheritance architecture, hierarchy. You can also declare members to be private, which means only the class itself can see it. Not even derived subclasses can see those members. If you do not know what I'm talking about, that's okay too, because I think these concepts are supposed to be introduced in CISP310. If you have taken 400 already, then you should know those concepts. But it doesn't really matter to us because a struct can only have public members. So everything has to be public and it cannot contain methods. Okay, so it's a very simplified, quote-unquote, primitive version of a class. It is a cookie cutter. It is basically saying, I'm defining a type. This type is called struct X, and it has two members. The first member is V. It is an 8-bit unsigned integer. And the second member is a pointer to a struct X. And that's it, okay? It only has two members. One is an unsigned 8-bit integer, and then the other one is a pointer to a structure. So do we have any questions at this point up to line 8 of the C code? No questions? All right. So then we're going to look at the subroutine link, which is from line 9 to line 13. It returns void. There's no return value. It takes two arguments, or it takes two parameters. PTR1 is a pointer to a struct X, and so is PTR2. And the only thing we are doing inside the subroutine is to change the pNext member of the structure that is pointed to by PTR1 so that it becomes PTR2. So are there any questions about line 11, the notation used on line 11? Any questions about that? It's all familiar to you guys? You know what that means? Okay, more or less?
You wrote it in the comment, so.
Hmm?
You wrote it in the comment, so.
Right. It also, line 11 can also express as line 12, which is basically saying the pointer notation here is a shorthand of dereferencing the pointer first and then accessing a member of the structure that is dereferenced. So those two are equivalent. Most people would use the format on line 11 instead of the format on line 12, but they are actually truly equivalent. So are we okay so far? Does everybody understand what the program or what the subroutine link is trying to do? It takes one pointer and it updates a member of the structure pointed to by the other pointer to that pointer. Yes?
Does it create like a linked list?
Yes. It is creating a link of a linked list. Yep. So if you don't know what is a linked list, that's okay too, okay? Because that is not required for this class. A linked list is a concept in CISP 430, which is data structure. But you don't have to understand linked list because I'm not asking you to write the C code for linked list or trees or anything like that. I'm giving you the code. Our only job in this class is to translate the C code into assembly code. So shall we move on to main from function link? We all good here? All right. So we're going to move on to main. Main doesn't do a whole lot of interesting stuff. On line 17, it declares two local variables, A and B. A and B are not pointers, they are actual struct X's, which means A has a member V, has a member P next, and so does B. Is that okay? So if you look at a struct X, the definition from line 3 to line 7 as a cookie cutter, line 17 is using that cookie cutter to cut out two cookies. The two cookies, one is known as A, and the other one is known as B. So are we still doing okay so far? Differentiating the concept of what we're defining when we define a struct and what we are actually doing when we use struct X to create local variables. Are we good? Okay. So where do you think A and B as local variables live in the entire program? They are local variables, and where do you think local variables live? The stack. Exactly. Very good. Okay, so how do we put a structure in a stack? We'll explain that later. Line 18, 19, and 20, they are just doing some initialization to the members of the two local variables. So I'm making the V member of the two local variables. One would take a value of 23, the other one would take a value of 17. Why those two values? Well, they're just kind of random values that I thought of when I wrote the program. Line 20 is basically putting a null pointer into the P next member of the local variable B, which is a struct X. Is that okay? So instead of using null, N-U-L-L, all in uppercase, it is perfectly okay to use a 0 because 0 as an integer, or I should say as a literal number, can assume any type, and the compiler can automatically understand that in this context you're looking at 0 as a null pointer. So it's okay not to have to cast it to a pointer before I do the assignment. For those of you who are kind of concerned about types and think maybe the compiler would complain about this, well, if that is what you're thinking, that's perfectly okay. You can always cast the 0 to a pointer to a struct X. So this way, no matter how stringent type checking you set up the compiler to do, it will always be okay. But it's actually not necessary. And then on line 21, we are passing the addresses of B and A as arguments to call link. And that's it. Okay, this is the entire program. Do we have any questions about this program? It would actually assemble, it would actually compile and run if you do it in online GDB. And on the line of return 0, which is line 22, you can actually observe what is in A and also what is in B. So I would encourage those of you who are kind of a little bit rusty in terms of your structures and pointers to do that in online GDB or whatever IDE that is your favorite, C, C++, your IDE. All right, so now we need to look at the implementation of this in TTP ASM. And if there are any questions about the C code, do not hesitate to ask, because it would be kind of pointless to try to implement this in assembly language if the C code itself is not fully understood. All right, so we start with the no op, just because of a bug in Logisim. And you can also see that I got the syntax highlighting to work, which is really kind of nice because, if I have something that is not going to be syntactically correct, it would actually highlight the entire line and say, I do not recognize this syntax. So I have to give it a label. It cannot check that the label main does not exist at this point. That is not something that the editor can do because it doesn't actually parse the entire program to make sure that labels are fully resolved. It just knows that, okay, there is something after JMPI. I think we're good. All right, so next thing we're going to do is to initialize the stack pointer. There's really no need to initialize the stack pointer to 0, just because when you reset the processor, all registers will start with a value of 0. But just for completeness, it's good to kind of remember that we have to make sure that the stack pointer starts with a reasonable value, and 0 is a reasonable value in this case. So link is a subroutine. I don't want to do any implementation right now, so the only thing I want to do is to put in the usual code to do the returning, and this is the return code. And I would also remind people, I think I might have said it on Tuesday already, is not to just look at these 3 lines of code and just go like, okay, this is how we do return. You might want to kind of keep reminding yourself what each instruction is doing and why combined as a sequence of instructions, it is actually doing the returning to the caller. Because by looking at these 3 instructions that way, you are relating these 3 instructions to what is on the stack, the agreement between the caller and the callee, and also the concept of returning to the caller as a high-level programming language concept. And that is what your final exam will be testing. Okay, so it's a good idea to keep practicing until you go like, yep, I know exactly what is going on. I know how to relate this to stack operation, and I know exactly how this relates to the original C code. All right, so we get to main. Main this time has 2 local variables, so I need to remember to allocate for those local variables. So the usual thing I do is, this is the high memory location, and this is going to be the low memory location, and I want to know what is on the stack, okay, what is supposed to be on the stack. And I asked that question earlier, and you guys already told me that local variables are supposed to be living on the stack, which means main, as quote unquote a subroutine, even though it really is not, is supposed to allocate the bytes in RAM in order to store local variables A and B. But I forgot one thing that is important, which is how do we define the struct X in assembly language? So that's what we're going to do next. So I'm going to give you the labels. X underscore 0, X underscore V is defined to be 0. This is defined as an offset from the beginning of a structure of type struct X to where member V is supposed to be found. So most compilers, unless you tell it otherwise, is going to allocate memory of a structure in a contiguous piece of memory. That one you cannot turn off. Okay, if you look at the structure in terms of how it is represented in memory, it is always one contiguous chunk of memory. What that means is, it is one piece of memory. It is not broken up into multiple pieces of memory. Okay, so that's the first one. The second one is most compilers would do what is the laziest approach, which is it will order the members in the same order as the members are listed in the definition. So that means the first member is going to occupy the lowest portion of the memory corresponding to the structure. The second one is right after that. The third one is right after that. And then the last member would occupy the highest portion of the memory uh, allocated to the structure. So is that okay? Is that concept okay? Does everybody understand what I meant when I said that? Okay. So because V is the first member, it is really literally at the beginning of the entire structure. So the address of member V is really the same thing as the address of the entire structure because it is the first item. And then we define the offset to P next. That is going to be X underscore V 1 plus. So this 1 here is referring to the size of member V. And since member V is an unsigned 8-bit integer, it only takes a 1 byte. So when we add 1 to the offset of X underscore V or the offset to V, now we get the offset to P next. X underscore size is the size of a struct X, and that's going to be the offset to the last member of the entire structure plus the size of the last member of the entire structure. Are we okay with these label definitions? Because this is really important. This is how we represent a structure in assembly language. The assembly language itself, most assembly language that I know of have no way to represent actual structures. So we have to rely on these labels to help us understand, how to interpret a chunk of memory when somebody said, yeah, that chunk of memory over there, it is of struct type X, okay, of type struct X. So this is how we can interpret, okay, what member is where within this chunk of memory? And how big of a chunk are we expecting when we see a struct X? Are we good so far? All right. So, given that we are okay at this point, we are now ready to declare, allocation or allocate local variables in main. So from before, we know that we want to allocate memory like this. A has the highest address and B is the next one. But this time, the question is, how many bytes are we talking about here? So can someone tell me what is X underscore size as a numerical value? Hmm? Two is correct. So that means I need to allocate 2 bytes for A because in terms of where or how the memory is utilized, the higher portion of the 2 bytes is P next, and then the lower portion is V, and then the same thing with B. So each line is representing 1 byte on the stack. So we can see that B dot V is at the lowest portion of the memory, the chunk of memory on the stack allocated for local variables, followed by P next as a member of B, followed by V as a member of A, followed by P next as a member of A. So altogether, they would take up 4 bytes on the stack. We need 4 bytes for the local variables of main. Is that okay? All right. So just like before, we would like to use labels to indicate how memory is allocated. So the way I do that is to say main underscore B is going to be 0, which is where the stack pointer is pointing to. So main B is also a label of an offset, but this time it is the offset from where the stack pointer points to in order to find the beginning of local variable B. So we have to be very careful now because there are labels defined to be offsets of members of a structure from the beginning of a structure, but we also have labels defined as offset from where the stack pointer points to when we need to access items on the stack. Are we good so far with those two different types of offsets? Okay, all right. So now we can say, okay, where can we find A? Well, A is going to be some bytes after main B, but it's not going to be 1 because B is actually a structure. A structure can have a few bytes. Okay, So in this case, I'm going to reuse the label of X size because that's exactly the purpose of X size as a label, is to define and let us know how big is a struct X. So if I add X size to main B, then I get to the offset of A, which is a local variable on the stack, from where the stack pointer points to. So we need one more label, okay, main LVS, which is local variable size, which is the number of bytes that we need to allocate for all the local variables in main. So that's going to be the offset to the last or the highest local variable plus the size of that thing. So now we have main underscore LVS. It would be 4 because remember, X size is really just 2 and main B is 0. So we basically are talking about 2 plus 2 here. So main underscore LVS is 4. We are allocating 4 bytes on the stack for the two local variables A and B. Any questions at this point? Any questions about what the labels are for or why they are defined the way that they are defined? Okay, no questions. All right, well, then we can move on. So as usual, I'm writing the code in a structured way. So I'm putting in halt first, and then go back and do the allocation and then the allocation. So the allocation is simply to make use of the LVS label. In this case, it's main underscore LVS. And then we subtract that much from the stack pointer because remember, when we need to allocate something on the stack, we decrease the stack pointer. The stack pointer is at the highest possible point when it is empty. And then we will basically do the same thing, and then we are adding the same amount to the stack pointer to deallocate the local variables. And then in between, I can now refer to the labels correctly because until I get to line 28, nothing is actually happening on the stack. In other words, the stack pointer D is still pointing at 0, okay? It has not allocated anything. So it's until we get to line 28 or until line 25 and 26, it'll happen that the stack pointer actually got adjusted to where it is supposed to be at. So we good so far? All right. So now we can look at the code in the C code on line 18. So we are looking at this particular line over here, and then we're asking, how do we implement it? The 23 as the right-hand side of the assignment, I'm not too worried about it, okay? So I'm more kind of concerned about the left-hand side, which is we're supposed to change member V of the local variable A, which is of type struct X, okay? So how do we get there? I think most people would agree that we need to get to A first, right? Because as a member of A, I cannot get to member V unless I know how to get to member A first. So we have to first figure out how to get to member A. And you will look at this code and go like, oh, okay, that looks really kind of familiar. So we are looking at LDI A with main A, add AD. So these two lines, the first one is loading the offset of where local variable A can be found relative to where the stack pointer points to into register A. Okay? The second line is adding the stack pointer to the offset. So as a result, on line 29, we end up with A being the address of local variable A of main. So is that concept okay? Because that's something that we have been talking about for more than a week, which is how do we find items that are sitting on the stack. So, but that would give us only the address of local variable A. I don't need the entire thing. I just need one member of the entire structure, and that member turns out to be member V in this case. So the second thing that I need to do is to add LDIB, register B is fine, with the offset from the beginning of the structure to the member that we need to access. So since we need to access member V, X underscore V is the label corresponding to the offset from the beginning of the structure to member V. So we are putting it into B, and then we add B to A. So now register A actually contains the address of member V of local variable A. Are we okay so far? Do we have any questions about this particular sequence of instructions? No questions? Okay, so here's the second question. The second question is, Tech, are you really sure it has to be like this cumbersome? Because what we are doing here, main A is a constant. It is a value that is already determined at assembly time. It is not something that we determine at runtime. So is x underscore b, right? So both of those are just constants. So in the end, what are we actually putting into A? Well, there are three components to A. One is main underscore A, which is the offset from where the stack pointer points to find local variable A. That's one component. We have register D, which is a runtime thing. It is the stack pointer. So that's the second item. And then the third item that we're adding to A is x underscore V, which is also just a constant. It is the offset from the beginning of a structure to member V of that structure. So we got three items. Two of the three items are constants. Only register D is a runtime thing. It kind of depends on what else is on the stack at the time. But the other two are constants. So we can fold the two constants into one single constant and be done with it. There's no need to do it like this. Okay, so what I'll do is I'm going to give you the alternate sequence of instruction that would actually do exactly the same thing, but it looks a little bit cleaner, but a little bit more confusing. So I can use main A here, x underscore v, also here, and add those two together, and then add AD, as a second thing. So I claim that the sequence from line 28 to line 31 is equivalent to the sequence from line 33 to line 44. There's absolutely no need to load another constant into register B and then add that register B to register A, because we can fold the constant of x underscore V onto the first line and it will accomplish the same thing. Are we convinced of this? Okay. So to fully understand this one, you kind of need some math background. It is called the commutative property of addition, which means once you have a big addition, the ordering of how you specify the things to be added does not matter. So are we doing okay so far with this one? Okay. All right. So if we're okay with this one, I will delete the first four instructions here because I prefer to make it a little bit more concise if I can. All right, so now register A has the address of member V of local variable A, which is of struct X type. So now all that is left to do is to put the 23 into register B and then do a st store AB. There we go. So I claim that line 28 to 31 is going to implement line 18 of the main of the C code. I can keep going like this and just test the program at the very end, but I'm not going to do that because I want to test the program right now. Okay? Because if this is not working the way that I thought it would work, I have no reason to proceed to write any additional code. Does that make sense to you? Okay. So now we're going to test the code and make sure that the program is working up to this point. And this is also how I would recommend you to write the swap program as well as the one that is due next Thursday. Is not try to write a lot of code, but to write a little bit of code, understand what it's supposed to do, test it, verify that it does what you think it's going to do before you proceed to write another chunk of code. So how many lines of code you want to write before you check it again? Kind of depends on your comfort level. Because if you are like me, okay, if I'm actually writing code, I typically want to write maybe 10 up to 10 lines of code before I test it. I cannot just stop at a certain point. It has to be one point where it accomplishes something that is verifiable. And this is at such a point, okay? I can now verify and go like, I think we got enough code here that I can check to see whether the program is working or not. In this class, okay, you have to understand what the whole thing looks like in terms of memory locations. In other words, if I were to run this code, what am I expecting to see in the analysis tab of the assembler? So what do you think? So what do you think is going to change to 23, or the hexadecimal version of 23 in memory? Which location of RAM is going to get changed? So looking at this code is not going to be very helpful unless you start to associate memory locations to these things. So this is, yeah, it is going to be FE, yep. Location FE is updated to the hexadecimal version of 23, which is 17, because 23 is 1 times 16 plus 7. So you're correct. That's very good. So to the rest of the class, this is what you do. Okay, this is location 255, which is also FF. Okay, so you can always say this is 55, which is, okay, this is at location 255, which is the same thing as whatever is at location FF. And this is at the next location, which is 254, which is in hexadecimal FE. And we are supposed to change A.V because we are trying to implement line 18. So this location FE should update to 17 in hexadecimal. All right, well, let's go ahead and check it, right? This is another thing that I want to kind of remind the class is you might want to get River Spider installed and configured because it will really speed up the process of debugging your program. Right there. And if someone is asking, but Tech, you never talked about River Spider or how to set it up. Well, the answer is yes, I did in multiple occasions. But just in case somebody is missing all of those occasions, here's another one. I actually wrote it, TTP ASM code execution tracing, and it would actually describe, how to do it manually, which is okay. I have done it manually for many years before I actually developed River Spider, so I know it's doable. Yeah, it's a little bit tedious, but once you do it a few times, it's just muscle memory. It's not too big of a deal. On the other hand, if you want the thing to be automated and want to use River Spider, this document here will also give you the link to download the zip file. And within the zip file, there's a README file. And then within the README file, there is a kind of lengthy instruction to set it up. It might take some people maybe 30 minutes or so to kind of read through the whole thing and set it up. But trust me, I think those 30 minutes will be well spent because when you are writing the programs for swap and also for whatever is due on Thursday, being able to verify the execution of your program gradually, which means you have to run it like after a few lines, run it again after a few lines, it's going to be very helpful. But I will not force people to do it. Okay, there's nothing to turn in to earn points or otherwise. Whether you install River Spider or not is entirely up to you. So, having said that, I am going to use River Spider because I got it set already. So I'm going to submit. I have to make sure that I save the program first because that's one of the things that I keep forgetting to do is to saving the file first before I try to run it. So this is struct.ttp asm. And I need to go find the assembler. And where is my assembler? Oh, I see the tab. All right, so it's all done. I'm moving the assembler tab to here so we can actually see what's happening. All right, so here we go. Okay, so this is verifying that the program did write 17 in hexadecimal to location FE in RAM. So we are good there. Now, beyond that, I can also see the stack pointer goes back to 0, 0. That's also good because that means the stack is balanced. I remember to deallocate the 4 bytes of local variables. All right, so this is good. Okay, And I'm doing this to illustrate how I would complete the homework assignment. If I were you in this class, I would do it in a very gradual way because debugging a program written in assembly language is not easy. It's not easy for you in a class because you're just learning this stuff, and it's not easy for any professional programmer either, because assembly language programming is very different compared to high level language programming. A lot of the tools that you have regular debugger simply does not work when you are trying to debug an assembly language program. Okay, so if that is done, that means the next line, which is line 19, is pretty easy, right? I mean, it's kind of the same format. So 5 lines here, copy over here. This time instead of variable A, we got variable B, but we're still looking at member V of the whole thing, and we have to remember to change the right-hand side value to 17, which is 1 in hexadecimal, and that should get it done. And then the next line is pretty much the same thing too, even though it looks a little bit different, because all we are changing is which member is being changed and what value do we want to put into that member. So it really is kind of the same thing. So I'm going to do the super lazy copy and paste again. We are still accessing local variable b, but this time we are using p next as a member, and then the value that we want to put over there is going to be a 0. Okay? So given this code, I'm going to test it again, okay? Because I don't want to make a stupid mistake somewhere and just ended up messing up this entire thing. So what we have done so far is, so now we have to look at this location. This is 253, which is the same as location hexadecimal FD. And then finally, this is 252, which is the same as hexadecimal FC. And we know what value we're supposed to find over here because this one is unknown. Okay, we did not initialize that. This one we know is supposed to be hexadecimal 17, which is 23 in decimal. This one is supposed to be 0, and this one is supposed to be hexadecimal 11, which is 17 in decimal. So up to this point, okay, if I run this code, I should expect those locations to be changed the way that I describe here. So this is verifiable, right? Because I can run the code and I can look at the analysis tab of the assembler and just double check and make sure these things are happening. So let's go ahead and do it. Make sure I save the code first, and then go back here and resubmit the program to River Spider. All right, and you can actually see the analysis tab updating in the background, and we can see 17. We can see the 11. Oh, okay. I just did the way I scroll, on my keyboard, makes it easy to kind of press the middle button, which is paste. So that's why I have to be careful about that. So let's double check. Okay, am I seeing things the way they're supposed to be? So we'll double check. Go back to the source code and compare against the comment. Yep. So we got everything. Okay. So that's encouraging. Okay, because this means that, yep, there's congruency between how I think things are organized as opposed to what the behavior or what the program is actually doing. All right, cool. So now we get back to the source code and try to implement some more stuff. So this time I'm going to call the subroutine. In other words, I'm trying to implement the call on line 21. And someone is going to say, but Tech, you did not implement the subroutine. That is correct. I did not implement the subroutine, but the subroutine does have the instruction to return to the caller, which is good enough for me, okay? Because I just want to set up the call, make sure I got the right items pushed on the stack before I even try to write anything in the subroutine. So we have to push the address of B followed by the address of A, and then the return address. Those 3 things need to be pushed before I continue execution in link. And then when it comes back, I have to deallocate the 2 arguments because otherwise they'll be sitting on the stack for no reason whatsoever. So that's what we need to do. So we have ADIA with main underscore B, add AD, and that's it, right? This is the address of B already. Because main B, as a label, is the offset from where the stack pointer points to local variable B. When we add the stack pointer to that offset, we got the address of local variable B. So all that is left to do is to push it on the stack. So decrement D and STDA. So now we have the address of B pushed on the stack. Now we have to push the address of A. And if you have been listening to me, even just today, you would know that, well, tech is going to be lazy and just copy and paste the code. The answer is yes, but, okay? So I'll explain the but in just a little bit, okay? So I'm going to change the way I explain this in this class compared to how I explained it in the Monday, Wednesday class. I'm just going to do it like this, okay? And say, okay, that's good, easy peasy. And now I just need to push the return address, decrement D, LD, I, oops, I, A with dot 5 plus, STDA, and then I can JMPI to the subroutine, which is called link. When I do come back, I need to increment D twice, and that's it, okay? All right, we'll test this program. And make sure it's saved. Yep, it is saved. We go to River Spider and turn it in again. There we go. All right, so this time, what are we expecting to see on the stack? Well, let's find out, okay? So what we are expecting to see on the stack at this point, okay, I'm just going to copy these lines, which is 15 to 20 to where we are pushing the address of B and A, okay? So we'll go ahead and paste that stuff here. 15 to 20, copied down here. Okay, there we go. Excellent. So we are pushing the address of B here. This is 251, which is in hexadecimal FB, and it is supposed to contain the address of B. All right, so what is the address of B in hexadecimal? Okay, so what am I supposed to see at this location? Location FB in RAM, what should be the content at that point? I mean, you're looking at the memory map here. Where is B? Where is the starting point of B as a local variable? I really cannot tell whether you do not know the answer or you know the answer but just don't want to let me know. Yes, go ahead. So line 47 is the first byte of B, right? Line 47. Okay, let me put the cursor over there. Okay. You can see how this is B.V, which is the first byte of B. So that means the address of B is FC in hexadecimal. I should see this on the stack because I pushed the address of B on the stack. Is that okay? And then I have to push the address of A. Okay, so I'm gonna kind of write down what it's supposed to be here. And then we go to location 250 because this is another push, and this is at location FA on the stack. But what am I supposed to see as the content? Because I'm supposed to have pushed the address of A this time. So where is the address of A? What is the first byte of A according to this bunch of comments? Hmm? FE. Okay, so FE is indeed correct. Okay. All right, so this is supposed to be the address of A. So I'm expected to see these locations changed in this particular way when I test run this code. The question is this happening? Of course, this is just foreshadowing, basically implying that it's not going to happen the way we think it should happen. Okay, so we'll go to the trace again, and then we want to see if that is exactly what's going to happen. So we got the 0, 0, that is the null pointer, and then we push the address of B on the stack. This is correct, right? So let's double check. Okay, let's double check against our expectation here. So we are locating FB. It's getting the content of FC. We're good over here. And then we go like this here. We are pushing the address of A next. And this time it didn't quite get the job done. In other words, we're expecting to see FE over here, and then we're only getting FD. The question is, why? Why? Well, there are at least two ways that you can find out why. Okay, the first way is to analyze the code itself and ask yourself, okay, does that make sense? Does that make sense? Does that make sense? The second one is to look at the code execution and figure out exactly why we got FD. So which way do you want me to go in this case? Because I can go either way. Do you want me to go more empirical, which is based on the trace of the code, or do you want me to go more theoretical, which is based on the program itself, or and also the assumptions of the program itself? Hmm?
Theoretical?
Theoretical? Okay, so we'll go the theoretical route, which is probably the better way because in your final exam, you have no way to go for the empirical way. Okay, but the empirical way is good from the perspective of it will give you a more hands-on method to understand the concepts. So when you are studying, remember we're going to spend 80 minutes in this class, which also means you're supposed to spend 160 minutes outside of this class. That is when you want to go for the alternate way to figure out the problem here. Okay, so the empirical way is to ask something is not right about from line 56 to line 59, which is supposed to push the address of A. So we'll have to question what is main A. Main A is a offset from where the stack pointer points to local variable A, right? But remember, register D, or the stack pointer, is not constant. It's not static. It can move around. So, um, so now your question is the assumption that the stack pointer is at the same place as where it points to right after we allocate for the local variable, is that assumption still true? Or did we change the stack pointer already so it's not actually pointing to the base of all the local variables? That is the question to ask. So how can you tell? I mean, if I were to ask you, um, how do you find out whether we changed the stack pointer or not? How would you respond to that answer? How would you respond as an answer?
Look at, are we doing any operations?
Look at things that can change D, right? Okay. So you look at things that can change D that is prior to line 56, but after we allocate, the local variables. That's a good chunk of code, but we're gonna take a look. Okay. So we're gonna take a look and we identify this is where we did the allocation, and we already knew this code is working fine, right? The initialization of member V of both local variables as well as P next of B, those are all working fine, okay? And when we look at all of this code here, do they make use of register D? Yes. Do they change register D? No, because add AD doesn't change register D, it changes register A. So there's nothing here that is changing register D. Okay. So now we move on to this section of code here, and then we ask before line 56, did we change register D? The answer is yes, we did. And which line are we looking at?
53.
Line 53. We decremented D because we had to push the second argument. So that means, there's one more byte between where the stack pointer is pointing to right now on line 56 to where we can find local variable A on the stack. Is that okay? So this is where we can go like, oh, okay, so this would fix it. We just have to add that 1 to compensate for the extra decrement D on line 53. And that was necessary. I cannot say, oh, let's just not do that. No, we have to do it because we have to push the arguments, in a backward order. But this way, I can compensate for that. Are we okay so far? So this is really tricky from a certain perspective because it means when you're writing your program, you have to keep track of where's the stack pointer pointing to right now? What is between where the stack pointer points to my local variables? Has anything else been inserted or been pushed in between? So you have to ask all of those questions, in order to kind of realize that it's not working. But you can also see how I can check for the mistake in the trace. Because in the trace, I was expecting FE to be here, but I see FD instead. It's not exactly what I want. And instead of just saying, oh, it's only 1 off, I'm just going to increment whatever I'm pushing here. That would fix the problem, but it doesn't address the reason why we have to do that. Is that okay so far? All right. You all good? All right. So with that fix, okay, for here. So with that fix, I think we are good here. Okay, so we are gonna go test the code again, and this is why River Spider is going to be handy because I can just fix one little thing, run the whole thing, double check, make sure it is now FE. We can actually see it live updating, which is actually quite gratifying. And we can now say, okay, so now we are pushing the right things on the stack. This 2D here, oops, this 2D here is the return address. I can double check this is the return address by looking at the assemble tab. So in the assemble tab, I can look up the increment D instructions and make sure that it is at location 2D. So this is indeed the correct place to return to. It is the right return address, 2D. So that means everything is happening the way it's supposed to. We went into the subroutine at location 05. There's not much to do, and then it returned to location 2D, and then it incremented the stack pointer twice, and then we deallocate the local variables, and the stack pointer goes back to location 00. Everything is good. Okay, so I know at this point I am now finally ready to implement the subroutine because I know I'm passing the correct parameters to the subroutine. I know the stack is set up correctly. The main program itself is sound. There's nothing wrong with main itself. So now I can go focus on just the subroutine that I need to implement. So are we still doing okay so far? Okay. In industry, I would not be doing something like this. I will be using Get, okay, or using GitHub or a localized Get here because this way I'm doing revision control. If I did one stupid mistake after a beer, that can happen. And with me, one can of beer has the effect for a few hours because I do not actually process alcohol very good. The alcohol, instead of being processed in the liver, it just stays in my head. So I'm a very cheap drunk because most people need a few beers, to get to that state. To me, it's just one beer, one can, and I'm already there. I stay there for a few hours. So if I write code during that time, its chances is I might actually mess up the program. So with revision control, if you do mess up the program where it is now in a worse state than it was before I got drunk, you go like, oh man, crap, this program is used to be working at least up to this point. It's now not even working up to that point, okay, because I might accidentally delete a line where the code was already working. So revision control allows you to compare the program to the last check in the repository. And then you can actually look at the differences and go like, that line doesn't make sense. Why would I make a change like that? You can just revert back to whatever you have stored last, in the repository. So revision control is not only for working in a team, even if you work as an individual, it can still be very helpful. All right, so moving on to finish the implementation. So now we need to go back to the subroutine because that's what is left to do. So we are only left with link to do. So right here, I want to look at what the stack is going to look like. So once again, high location, low location, and I should be expecting to see PTR2 over here, PTR1 over here, the return address over here. I do not have any local variables in this case, so I don't need to allocate or deallocate for the local variables. And then I define labels, so I can refer to the labels instead of having to remember where things are on the stack. So in this case, I am going to do something like this, okay? Even though we have no local variables, so instead of saying there are no local variables, I can always say, we need 0 bytes for all the local variables. It says exactly the same thing, but this allows me to use a much more generic template of code if I need to write subroutines. So I'll explain that in just a little bit. PTR1 is going to be link LVS 1 plus because we have to skip over the return address. And the PTR2 is link PTR1 1 plus. So now I have the offset from where the stack pointer points to the various items on the stack, which in this case is really just the 2 parameters because we don't have any local variables. So I'm going to do the usual thing, which is allocating for the local variables. I know it doesn't sound like it makes sense because in this case, we really do not have any local variables. But at the same time, if I choose to have local variables later on, I don't have to go back and say, do I have to remember to allocate and deallocate for the local variables? Because it's already allocated. I don't have to worry later on if I need to have local variables at a later point. So I'm already thinking about the future. This is all based on years of experience. Yes, I'm kind of old compared to all of you, or even your parents. Um, but this is from years of experience. Okay, if I don't do something like this, and later on I need to change the program to accommodate for local variables, it's harder for me to find out. Okay, I need to allocate here and then deallocate over here. All right, so now we can work out this code over here. So we need to get to PTR2. So typical way is to load the offset into register A. So this is link underscore PTR2, add AD, that's the address of it, and then load AA. This would be the actual value of PTR2. So I got the right-hand side done. And if you are kind of concerned about, I'm not sure whether my code is right or not, well, run it again, okay? But you have to understand what you're supposed to see at this point, okay? So I'm going to demonstrate because this debugging technique or technique of writing a program in a very gradual way can, in the end, save you time. All right, so save the code and run it again, okay? So I'm going to run the code again. But I have to know what I'm looking for in order to double check and verify that the program is doing what it's supposed to be doing. So I have to focus on the instruction corresponding to line 25 and make sure that what ends up in register A is indeed PTR2, which is also the address of B, which according to our picture down here, the address of B is FC. So on line 25, when we do get to line 25 in the trace, we're expecting to see FC in register A. Is that okay? Are we doing okay so far with that analysis? We good? Okay. All right, so now we get to the trace, and this is also, kind of nice because I added column F and G. So all you have to do is to locate line 25 and then look at, the result of line 25. Yep, register A did get FC, which is the address of local variable B of main. Woo! Yes. But if I don't check this, okay, if I do not check this and just proceed to write additional code, then when the program doesn't work the way I supposed, that I expect it to work, I would have a lot more lines to check and go like, okay, which line is responsible for this problem? This way, I know the program is working 100% correctly up to line 25. I got the right hand side value into register A. Is that okay? So now we are going to deal with the most difficult part of this entire program, which is the left-hand side of line 25 of, not line 25 because the C code has a different line number. So we're looking at line 11 here. The left-hand side is the trickier portion. It's not insanely tricky. It's just a little bit more tricky. So the first thing we need to know is what exactly are we referring to on the left-hand side of the assignment on line 11? That's the first question, because if that question cannot be answered, there's no way we can actually figure out how to do it. So the left-hand side of line 11 in the C code is referring to pnext as a member of the structure that is pointed to by ptr1, which itself is a parameter that is living on the stack, and the way we get to it is an offset from where the stack pointer is pointing to. Yes, that was a very long run-on sentence, but I can actually repeat that. Do you want me to repeat it? Yes? Would that help? I don't really think so, but I will go ahead and repeat it. We are referring to pnext as a member of a structure of the type struct X that is pointed to by ptr1. ptr1 itself is a parameter, and as a parameter, it is sitting on the stack, and the way we get to it is by the offset from where the stack pointer points to the parameter ptr1 on the stack. Is that helping? I'm not an audio learner, so if somebody is to just tell me something, in words, it's like I can process the first 5 words out of that entire sentence. The rest all becomes, if you have ever watched Snoopy or the Peanuts, as an animation, Snoopy can interpret his own name, and then everything else is like wow, 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 wow. That's exactly what happens after the 5 word of a sentence that somebody is speaking to me. Okay, so the best way to do this is to draw a picture. Okay, um, you can probably draw that picture yourself. Okay, so let me take a look at the stack here. So if you want to draw a picture, I suppose I can use ASCII code to do something like that. It's not going to look good in any way because it's just an approximation. This here, okay, the address of A, this is parameter PTR1, and this is parameter PTR2. In other words, this really is a pointer to the structure A, which is a local variable. This is a good way to burn some minutes in the class time. Oops, one more. There we go. There we go. Because it is a pointer, okay? Its only job is to say the structure that we want to modify is over there. Is that okay? And then the stack pointer is pointing here because that's the last. Actually, I take it back because we also have the return address. So the return address is pushed here, which is 249, which is in hexadecimal F9. And I have no idea what it is because we keep changing the program. So this actual content is, we don't know what it is, but we know the stack pointer is supposed to point here because we do not have any local variables. So now the question is, how do we get to the pointer itself? If all we have is the stack pointer, the first thing we need to do is to go, oh, stack pointer, you are close to what we need, because what we need is just 1 byte on top of this. That is the offset to the parameter. So we get there first. Once we get there, we retrieve the value at that location, which itself is a pointer pointing to local variable A of main. Once we get there, then we say, I need to change not a dot v, but a dot p next. Where do I find a dot p next? Well, we just have to add the offset to member p next to the beginning of the entire structure, which is the address of A of main. So those are the steps that we need to perform in order to accomplish what we need to do with that line of code. So this is how we do it. I cannot use register A because it is the right-hand side of the assignment on line 11. So we're going to use register B. We first get to PTR1 as the address of PTR1, which is the address of the parameter. Then we do one LDBB to get to the actual PTR1. So now register B is a pointer to a structure. But we don't want the entire structure or the first byte of the entire structure because we want a very specific member of that structure. So now we have to use LDIC with the offset to the member from the beginning of the entire structure, which is x underscore p next. And then we add that to B. So register B now actually contains the address of member p next of the structure the PTR1 is pointing to. So that means we are now ready for the actual store instruction, store B, and I think A is the right-hand side. So I think this code is going to work, okay? Maybe, maybe not, right? So this is another run of the code using River Spider. So we get back to River Spider and say, let's do it one more time. And then we get back to the trace. And this time I can focus on the lines that I just added. So line 27 to line 31 or line 33 are the ones that I'm concerned about. So we can keep going. And I think I forgot to save the code again. Yep, I forgot. That little plus sign over here, that's an indication that I changed the file but have not updated yet. Okay, so we're gonna run it one more time. Okay, excellent. So now we can get back to here, and then we can now check. Now, if you want to be impatient and just want to say, did we store the right thing into that location? You can kind of skip ahead. And this is what we put into location FF, which is FC. So the question is, are we actually putting the address of local variable B to the P next member of local variable A of main? That's the question, right? So to double check that if we really are doing what we're supposed to do, we go back to the stack picture and then we take a look. I mean, even this one is fine, okay? Because according to what I think the program should be doing is we are putting the address of B of main, which is FC in hexadecimal, to P next of A, which is at location FF. So that means location FF should now have the value of FC. Is that making any sense? And according to the trace, if I remember correctly, that is actually what we did. So we can see that we store FC into location FF. So it got the job done. Now it's time to double check and make sure I did not mess up the rest of the program, which means, did it return back to main correctly? Yep, it returned back to main. And then we adjusted the stack a few times. It went back to 0, 0, and then we get to location 4, 4, which is where we find the halt instruction. So the program did work correctly at this point. So are there any questions about this program, the code itself, the approach, or anything related to this entire process. Oh, I have a question. Do people actually write programs like this? Why? What is the whole point of writing code in assembly language and be able to communicate with C code using structures and all that stuff? Tech, you must be just making all this stuff up to make this class as hard as possible. Go ahead.
It's incredibly memory efficient.
It is memory efficient, and there are times where you cannot write code in C. You go like, why? Well, imagine you're writing a real-time kernel. You're writing the operating system itself. How do you write an operating system itself entirely in C? A good portion can be written in C. I would say Linux is, I think the last time I checked, is like 90 something percent is in C. So, but you still have 10% that cannot be written in C. Because who's going to set up the stack? If you write code in C, you're making the assumption that, yes, we have a healthy stack, we have a stack, and then everything else is already taken care of. Well, who's taking care of all of that stuff? It cannot be written in C. I can actually show you an example of something that I have done that illustrates the importance of being able to do what I demonstrate in this class. So I think it's under develops. Nope. Okay, let's go to the home page. Nope. Where did I put that? Okay, I can. Uh, all right, so let me double check because it's. I do want to kind of demonstrate or at least show you that. All right, so public HTML. Yep, it is develops. Develops has its own.
You put developer.
Hmm?
You put developer, not develops.
Oh, did I? Okay. There we go. Thank you. So this is a real-time kernel. I actually wrote the real-time kernel. So you might be asking, so exactly what is a real-time kernel? It's a very tiny operating system, and you might be asking, how tiny are we talking about? 2 kilobytes, 2,000 bytes. Okay, that's the real-time kernel. But what does it do? I mean, why are you writing this? This allows me to do multi-threading on a MCU or microcontroller unit. So it's one of those things that live on an Arduino board, okay, which by itself does not know how to do multi-threading. So without multi-threading, which is a way of saying this function, and this function here, they're all happening quote unquote at the same time. So real-time kernel gives you the pretense that things are happening at the same time, the functions are all quote unquote executing at the same time, and this thing has a lot of features. It has priority queues, which means you can say this function is more important than that one, and that one is more important than that one. So it's for embedded controllers, where certain things you have to do it right away. For instance, if you have a gripper that's trying to catch something that's falling, and you have an interrupter that can detect whether something is passing through the sensor, you have to respond within a certain time. Otherwise, you're not going to grip the object that you're trying to catch. On the other hand, you might have a user interface that's using a serial connection and whatnot. I mean, if you're like a quarter second late, coming back with a reply or printing something on the screen, it's not the end of the world. The end user does not even notice. So you have something that's really high priority, and other things like when we get around to it, we can do it. So it has priority queue, and then when you write code in a multi-threading environment, you can either do what we call yielding, which means I get to a point where I can yield control to some other thread to continue execution, but that is cooperative multitasking, which means if somebody decides not to be cooperative, that function can hog all the processing power, and nobody else get to process anything. Okay, so this real-time kernel has what we call time slicing, which means Okay, I'm going to give you up to 10 milliseconds to do whatever you want to. After 10 milliseconds, I will do quote unquote a preemption to basically take control away from one thread and say, you have used up all your time. It's time for somebody else to start to run. It also has semaphores, which is a way for synchronization between the threads. Because there are times, especially when the multiple threads need to access the same data structure, you don't want those accesses to be interleaved in a certain way because that can be very bad. So semaphores is a primitive way to make sure that threads do not try to get into the same thing at the same time. So it has all of those features. It doesn't have a file system, and this entire thing was written in assembly language. But the point is, it is written in assembly language, but it does interface with C code. So the rest of your program can all be written in C code. You just have to call the API calls, to this thing here. So all of these are basically just there's a structure, and the function calls refer to those structures. But when you look at this, okay, this is just an example. So this particular subroutine is actually entirely written in assembly, but you can call that from C code. And this is why I think it is important for some people at least to learn how to write code in assembly, but they can interface with C code. In other words, C code can call the assembly code. The assembly code know exactly what the structures are, how to access the members of the structure, and then the assembly code in return might need to call C functions too, because do you want to re-implement everything? No. So if there's a C function to do something already and you're in your assembly code, you just go like, I think I'm just going to call that function. So the percentage of people who do this kind of work is fairly small. Okay, I would say no one in Twitter needs to do this. But the people who do this kind of job, they are very specialized. It's a very niche kind of area. But at the same time, it's also very flexible in terms of what it can do because someone can give you a raw processor and say, okay, we need to write all of these complicated things on this processor. You go like, does it have an operating system? No. You go like, okay, fine. Instead of going like, oh, it doesn't have an operating system. I need something that at least run Linux. I mean, that's a lot of resources. So this is just a context of why I teach this class the way that I do. Okay, and also if you guys are interested in something like this, this is it belongs to embedded system programming, um, and there are a lot of possibilities in that particular subfield of computer science. Alrighty, so I'm done with today's lecture, and I'll go ahead and release the lab activity for today, which is really short. The one lab for today is really, really short, but the assignment, the actual programming part of it, is not short. Okay, so you need to make sure that you allocate enough time. So the lab for today is called Making Simple Use of Struct, and I will make it visible. And let me see if it has a passcode. And according to this, the access code is Constructicon. This is a reference to transformers. Constructicon. Pro? Nope, not Pro. Okay. And you have until, oh, I have not yet specified. So you have until noontime to turn it in. I mean, there are only two questions, okay, and they're multiple choice. So I think if people want to use the infinite monkey approach, they can, but that kind of defeats the whole purpose of the lab. But I have no objection of people shooting themselves in the foot, as long as mine is not close to it. All right, so we got two labs due today. This is the new one, and then the one from Tuesday. I also make it postpone the due date to noon time today. So for those of you who need some more time to get it done, you can do it today. All right.
you made the lab on Tuesday and due today. I thought you meant the submission.
We're doing
Did he
the-
email you back?
Oh, no,
Now we
submission
have
is due
to-
next week. That's
Oh,
why I was
yeah.
confused for a second. I was like,
No,
oh my gosh,
that
like
was
less
for-
time than I thought.
Oh, so yeah.
The code itself is due next Tuesday.
I thought you were saying the code was due today, and I was like, oh my gosh.
Oh, did I misspeak? Did I misspeak again?
No, that was me.
Oh, okay. Because I'm famous for that. Infamous.
Constructicon? What's a constructicon?
Oh,
It's
is
from
it true? Constructicons? Okay, let me. Oh, Constructicons. Right. Okay. There we go. You can look up Transformer Constructicon. It's actually from that show. There you have it. $264. Wow.
I thought you were talking about like circuit transformers or whatever.
No, it was Constructicon. The voice behind Optimus Prime is actually continuous. It's the same voice actor from the original series all the way up to, I think, pretty recent ones. Because nobody else has that kind of deep voice for Optimus Prime. Autobots wrote out.
Fingers, actually. What? Oh, go on. Global printer variable. Wait, hover over the.
Yeah.
Wait, what? Doesn't it have like? Oh, RAM.
Do you remember what the access code for the function calls lab was?
That's read.
Let me
I
check.
remember the first one was frame.
Swap.
Swap?
Yeah. Which is also the name of the function that you need to compute.
How about we split up? It's B. I put it just it's a 2 question. Oh, okay. 2 out of 2. first one? How'd you get the first one?
Yeah, like your mom.
Your mom? Bro. What? What'd you put the first time?
But 8 because each one has 4. I thought each one had 4, but I was reading it wrong.
Okay. Cool. We're done.
Oh, hey, Tech.
Mhm.
Today's lab, or not today's lab, today's lecture made way more sense than Tuesday's.
Say that again.
Today's lecture
Mhm.
made way more sense than Tuesday's.